Hey guys, welcome back. So we're finishing up 3.2. We have two examples left, example 6 and example 7, and we're going to go ahead and tackle example 6 right now. So we have the integral of tangent cubed x dx. So the problem with this one is that there's no powers of secant. So when this happens, what we want to try to do is actually pull out a tangent squared, which seems weird because we're like stripping off, or we're like siphoning off something that's a little bit larger than what we've done in the past. Well, actually correct that, because when we had like secant to the fourth, we broke that up as secant squared and a secant squared. So it's honestly not that unordinary, but that's the way that we're going to run with this one. Okay, so having that said, I'm just going to do this right here. So we have tangent cubed x, right? We're going to break this up so that we have tangent x times a tangent squared x. And the reason why I'm going to do that is because I'm going to take my identity for tangent squared and I'm going to use it. So tangent squared is equal to secant squared x minus 1. So having that said, let's go ahead and input it here. So we're going to do tangent squared is equal to secant squared x minus 1. So there's the identity. Okay, so now having that said, you guys can see that we obviously now have a secant, which is what my original problem was. So my integral, let's rewrite it. Let's rewrite it with what we have now. So instead of the integral of tangent cubed x dx, we're going to have the integral of this right here, what I'm underlining. So we're going to have tangent x times secant squared x minus 1. And then we have a dx. So let me put this in parentheses. There it is. Now what I'm going to do is I'm going to distribute. I'm going to take tangent and I'm going to multiply it in here. Okay, so having that said, let's finish that off. Let's do that. So if we do exactly that, we're going to have tangent x times secant squared x and then minus tangent x dx. Okay, how does this help us? It kind of looks more gross. Remember that if we ever have terms inside of our integral, we can break that up into two separate integrals. So that's exactly what we're going to do now. So let's do a purple integral. Let's do that first. So our purple integral is going to be this first part. It's going to be the integral of tangent x secant squared x dx. Okay, and our other integral, we're going to leave the negative sign in the middle. And then our other integral is going to be our, I don't know, it's going to be pink. There we go. So then we're going to have the integral of tangent x dx. Okay, let's do our purple integral first. So there's a couple ways that you can do this. Like I said previously, there's usually always more than one way to do these types of problems in terms of math, in general, in life. There's more than one way to do everything. So just because I say to do something one way doesn't mean that you can't explore and figure out how to solve your problem in a different approach. And I implore you to do that. It's what makes a good math student. So in this case, in the notes, I do it one way. So you can take a look at that. I'm going to do it opposite the way that I do the notes. I make a mention of both methods in the notes, so you shouldn't be like completely lost in this approach here. But I'm going to go ahead and say that in this case, I'm going to say that so let's do this in yellow. I'm going to say that u is going to be equal to tangent x. This is actually the faster approach. Okay, then du is going to be equal to exactly what we need it to be, secant squared x dx. Having that said, let's go in and replace everything with u and du. So in this case, we're going to have u du. Beautiful. Now if we finish this off, we're going to end up with 1/2 u squared plus c. Let's replace what u is. So we have u, right? And so that's going to be tangent squared x plus c. So we finished off one part. That leaves us with going over here and tackling our pink integral. So we still have our minus sign in between, which means I'm just going to like copy this down here. Our minus sign is going to be here. Let's go ahead and take care of this part. So in this case, tangent x, it could be a little bit troublesome at first. Maybe you, if you do come across this, you'll be like, oh crap, what do I do? Remember that you can always rewrite tangent in terms of sine, cosine. So if that was your first instinct, great, congratulations. That's exactly what I'm going to do too. So I'm going to rewrite tangent so that it is sine x divided by cosine x. And then we have our dx there. Cool. Now we're going to do a u sub. So I'm going to say that u is going to be equal to probably cosine. And then du is going to be equal to negative sine. Now instead of leaving that negative there, I'm going to bring it over so that I have negative du is equal to sine x dx. And now I think I'm ready to go ahead and substitute. So I'm going to have basically u on the bottom, right? And then I can write negative du up here if I'd like. Now let's bring that negative to the front. So we have negative, and we have du divided by u. That looks kind of weird to write, so if you wanted to, you could rewrite this as 1 over u du, just to kind of help you see it in a little bit different manner. Now that I've done that, though, hopefully that'll jog your memory as to what 1 over the variable is in terms of finding its antiderivative. It is ln of u, right? So I have the negative out front, and then I have ln of absolute value u plus c. Now, we can't leave it in terms of u, right? We have to write it in terms of what the original variable was, which is x. And so if we do that, if we rewrite what u was cosine, right? U was cosine x, and then plus c. Okay, so if I zoom back out here, I have my purple answer and I have my red answer, and I want to combine them to give me my final answer for this entire problem. So if I write down what my final answer is, I'm going to combine them. But before I do that, I want to be mindful of two things. First, I want to be mindful of the fact that there's a negative sign in the middle here and that there's a negative sign out front here. So be mindful of that. However, I don't know if you guys have looked at my notes. If you have, you might have been lost. But there's a way to rewrite this here. Now, remember, this is a logarithm. So we can bring our power back on top here. So we can actually rewrite this as ln of like cosine x to the negative 1/2. And another way of writing that, like cosine x to the negative 1/2, you can rewrite that as ln of 1 over cosine x. And if you guys remember, what is 1 over cosine x? 1 over cosine x is actually secant x. So in my notes, I didn't explain how I got that, but hopefully that makes sense to you guys now. So now that I have that simplified over there, I still have my negative out front, and then I have my purple side that I'm going to go ahead and copy down right next to it. So I have 1/2 tangent squared x plus c. Now if your question is what do I do with the plus c's, just add them together. What is a constant plus a constant? It's just a constant. So if you wanted to differentiate, let's say that we called this left one c1 and we called this other one c2, we would just say that c1 plus c2 is equal to big old C. Some constant plus another constant is equal to another constant. Who cares what they are? I don't. Let's just call it C. So in that case, I'm going to erase all of this stuff. Actually, let me just keep it. I'll keep it. Let's go ahead and go down here and copy everything. So my final answer, let's do this. So my original integral, what was my original integral? My original integral was the integral of tangent cubed x dx. The answer to that is the following. It's going to be 1/2 tangent squared x minus ln of secant x plus a big old C. And that is it. That's our answer. Cool. So hopefully that made sense to you guys. Let's move on and talk about our next example, which is our final example. Thank God, right? So we have example 7. So example 7 can get a little bit annoying. So powers of secant can be a little bit annoying. Powers of anything can be kind of annoying. So First and foremost, this integral, as you guys can see, it doesn't have any powers of tangent. So we need another way to approach this. Also, the power of secant is not even, so we can't even try the strategy that we had previously used. What we're going to do is we're going to go ahead and do this problem by integration by parts. Believe it or not. So, all right. Before we do that here, I am going to, first and foremost, zoom in. So we have our original integral there. I know that we're going to do this by integration by parts. What we're going to do, let me go ahead and rewrite my integral so that I have it represented a little bit differently. So I'm going to have secant squared x and then secant x. I'm just going to siphon off one just so we can take a look at this. Now we're going to do integration by parts. Again, this isn't super intuitive. I'm just telling you this is what we're doing so that you can kind of see the process here. But a lot of these things, kind of what I showed you, a lot of the stuff that we're learning isn't super intuitive. These are just techniques that you're picking up and you're going to learn to apply them, and you're going to learn to identify when to apply them. So it takes some practice. It takes practice, guys. Okay, so integration by parts, here we go. I'm going to say that u is going to be equal to secant x. And then the derivative of that, so du, is going to be secant x tangent x. And of course dx. Okay, having that said, what did we have left over? Well, this is what we have left over. We have secant x and we have dx, right? We have those left over from our original picking of the u and the dv. So that means that the dv is equal to the parts left over. The parts that are left over are secant squared x and our dx. Okay, now what we're going to do is we're going to take the antiderivative. We're going to find the antiderivative of that, right? And we're going to call it v. So the antiderivative, when you take the derivative of what, you get secant tangent, right? So when you take the derivative of tangent, you get secant squared. So if you're going backwards, this would be equal to tangent x, right? Okay, beautiful. So there's that. So now we know what u, du, dv, and v are. So now we're actually ready to go ahead and rewrite this. Okay, so I know the way this is going to go, so I'm going to go ahead and write my original integral over here. I'm going to try to keep this nice and neat for the most part. So my original integral was the integral of secant cubed x dx. Okay, so now I'm going to do my uv minus the integral of v to u. I'm going to fill that out right here. Okay, so u is secant x, v is tangent x. Not too bad. Okay, so minus the integral now of v du. So that's going to be tangent x, and du looks kind of ugly, right? What is du? So du is going to be our secant x tangent x. And of course our dx. Okay, so what can I do here with this piece? So what I am going to do with what I just created is I'm going to go ahead and combine my tangents by multiplying them together. So if I do that, let's see, I'm going to copy from here. So I have secant x tangent x minus, let's write this out like secant first, and then we'll have tangent squared here. Cool. All right, so having that said, using identities, I know that I could probably, if I wanted to, rewrite tangent squared in terms of secant squared. So I'm actually going to do that. I'm going to do that now. Okay, so let me go ahead and rewrite another line for myself. I'm just going to copy down all this stuff that's not changing. All right, And then now I'm going to go ahead and rewrite my identity. I'm just going to write it in red so you guys can see which part I'm actually substituting. So tangent squared x is going to be replaced with secant squared x minus 1. And then we have our dx. Awesome. Okay, so how does that help us, you may ask? Well, before I rewrite, I'm going to do another simplification. I'm actually going to multiply secant into here. I'm going to multiply it in, I'm going to distribute it. So let's go, let's do that. All right, so rewriting all the stuff that doesn't change, I still have secant x, tangent x out front, minus the integral. Let's go ahead and multiply out, so we end up with secant cubed x minus a secant x. And then, of course, we have our dx. Okay, so like I told you guys before, if I have two terms in an integral, I can break it up and rewrite it as actually two integrals. And that's actually what I'm going to do here. So, okay, let's do that. So continuing to rewrite the stuff that doesn't change, I have secant x, tangent x. Now, if I'm just going to leave it like this. So let's see, I have the integral secant cubed x, and so one thing that I want to be careful of here is my negative signs. So notice, I'm going to write this in red, notice that there's a minus in front of this whole thing. So if I break up the integral, I want to do it in such a way that I'm not going to change the nature of the sign distribution. So if I break it up into its own separate integral, I want to make sure that if I was to distribute, I'd end up with the proper sign. So if I break this up, I'm going to say that this would actually become a positive secant x dx. Okay, so now I have that. If you guys recall, we have actually in this lecture, or maybe in part 1, we simplified this already. We know what the answer to this is. The answer to that was ln of secant x tangent x, close my absolute value. That's what that was, and then like a plus c, right? So I'm going to take that piece of information and I'm going to input it there. So I'm going to have like one piece of this integral solved, or actually the last integral solved for myself. So let me go ahead and rewrite this. So I'm going to have secant x tangent x minus the integral of secant cubed x, and then I'm going to actually just write this answer here that I have in yellow. I'm just going to bring it up. So ln absolute value of secant x tangent x. Erase this stuff, and then we'll close our thing, and there we are. And I can add a plus c. I'm going to take care of the plus c in a second, so just bear with me. Okay, so this is what I have so far. If you guys notice, this thing is still going to be equal to, so let me go ahead and write this over here. This is still going to be equal to the integral of secant cubed x dx, right? So that's still there. And the thing that I want to point out is if you notice on the right-hand side has a secant cubed x, and the left-hand side also has a secant cubed x. So let's just call, just like we did in the last time, what was that, integration by parts, we had something that was cyclical. Let's call this integral I, and then let's call that same integral I over here. So we have like two variables there. Okay, let's go ahead and collect all the i's on one side, which means that we're going to, if this is a negative I, let's add I here. So that means we're going to have 2i is equal to secant x tangent x. So it's going to be equal to secant x tangent x, right? And then what do we have left? Well, we have plus ln absolute value of secant x tangent x. Okay, there we are. Now let's go ahead and divide both sides by 2. So if we divide both sides by 2, we're going to end up with I is equal to this term divided by 2 and this term divided by 2. So what does that translate to? Let me give myself a little bit more space. We have I is equal to 1/2 secant x tangent x plus 1/2 ln absolute value of secant x tangent x, close my absolute value symbol. And then, so I is obviously standing in place for our integral. So let me just go ahead and rewrite what I is. I was standing in place for secant cubed x. So that's going to be equal to all of this. And then I will close my absolute value symbol. Okay. And then, yeah, so you could add a plus c if you'd like, because there is technically plus c's in there. Plus c's, sorry. So you could add it. But there you are. There is secant cubed. So, kind of gross, not super intuitive. Again, this is like a cyclical case in the sense that you are able to eventually have your left side of your equation equal to your, or part, let me rephrase. You have part of your right side of your equation equal to the left side of your equation, and then you can actually like solve. So that's kind of cool, I think. Let me go to the last page here. Last page is a table of integrals so far. So things that you would have seen, things that you've done before, and then some trig that you've seen before, maybe in Calc 1, and then some things that we haven't really like done too much of, but definitely things you've seen before in Calc 1. So having that said, hopefully this didn't scare you guys off. It can get pretty hairy, like stuff like this. Obviously it looks kind of intimidating, but like I said in your integration by parts video, please be careful with your handwriting. It's like the biggest tip that I could give you guys is just try to stay as organized as possible, because your problems are going to get long. If you have bad handwriting, it's really going to hurt you guys if you don't have the ability to kind of follow your work and make sure that you are staying organized as possible. Might sound kind of crazy to say, or like I'm harping on something that may seem obvious, but I promise it will become even more obvious when you are doing your problems. Okay, so that's all for now. Hopefully this wasn't too painfully terrible to watch. Let me know if you guys have questions on 3.2. I'm sure you will, and I will be here to answer your